Alright, let's talk about the torsional strain of cyclohexane. When you draw the chair conformation of cyclohexane, with your axial bonds going either straight down or straight up, and your equatorial bonds going off to the side, whether that's to the left, to the right, or in the middle, the thing is that you actually have two ways in which this chair conformation can be drawn. If you look at the extremes, so the leftmost portion and the rightmost portion, you could start with left pointing down, right pointing up, or quite the opposite, left pointing up and right pointing down. Now you might say, well, that's just basically the same molecule, you simply rotated it, on its own axis. But turns out to be the case that these two are different conformations of cyclohexane. And there's experimental evidence that definitely shows you, yeah, there's an equilibrium that allows this chair conformation to be turned into the opposite chair conformation. And if you basically look at something like NMR that we'll talk about later in the class, you can look at the signals of the protons, the hydrogens that you have here. And at room temperature, actually, this is not even room temperature, this is 0 degrees Celsius. You see that all of the hydrogens in this molecule are equivalent, and that's represented by the fact that you only see one single peak in this spectrum. And that's, respective if you're axial or equatorial, which may look kind of weird to you because you're like, well, the axial hydrogens look different, definitely different than the equatorial hydrogens, just in terms of where they are positioned. But as you cool down the solution, and this can be done using liquid nitrogen um, temperatures, and cryoprobes, as you see right here. As you lower the temperature down, eventually you end up broadening this signal, and at one point you have what we call the decoalescence point, in which that single peak that we started with at the higher temperature, 0 degrees Celsius, at the lower temperature, it basically starts separating, and at one point, down to 222 Kelvin, so that's definitely negative degree Celsius temperature, you finally see the two separate signals, one for the axial, one for the equatorial. And what this is kind of showing you is that there's actually an equilibrium that makes the axial hydrogens become equatorial hydrogens, right? So notice that the red ones here are equatorial on the right structure, but they were axial to begin with. So this rapid motion averages out to a single peak. The nuclear magnetic resonance, or NMR, timescale is actually rather slow. So events like this, where there's rotation and exchange of conformations, sometimes get missed, at least at room temperature. But if you do cool down the solution, you could actually see those differences and inequivalencies in each one of the structures. So that's kind of nice to see. Now, in essence, what we're looking at here is two different kinds of conformers, and they will give us different energy profiles depending on what the groups are, right? In the case of cyclohexane, everything is hydrogen, so these two molecules have the same energy profile. But as you'll find out in a little bit, once we start introducing substituents onto the cyclohexane ring, we're going to have a different picture altogether. Now, before we get into the analysis of the conformers, the one thing I want to show you is that the conversion of one cyclohexane ring to another is definitely not that of just rotating the molecule on its own axis. What's actually happening is that the single bonds are rotating, but because you have a cyclic molecule, there is restriction as to how much you can rotate it. So the chair conformation, and we start with the bottom left and upper right, in terms of the shape of the chair conformation. What basically happens is that as you rotate the bonds, you could end up raising this corner on the left side upwards, yielding what we call the half chair conformation. So this is basically, this section here on the left side is technically flat, and it's only this thing that's kind of pointing out. And then what happens once you get to the half chair conformation is that a different corner, the adjacent corner can twist downwards, right? And this is just as a result of the rotation of those single bonds. So you can, as a result of that rotation, you can twist it downwards, and we get into what we call the twisted boat conformation. So notice now that bringing this down kind of like has this crisscross effect on those bonds, right? So this is what is technically referred to as a twisted boat. And continuing that rotation business, you could actually bring down the corner, this blue corner of the molecule, until you get to the regular boat conformation. And what I want you to notice right here is that you have one end of the molecule exactly lined up with the opposite end of the molecule, and of course these guys are lined up with each other, and same thing for the back portion of the molecule. Now continue on the process. If you continue semi-rotating those single bonds, what you could do is now twist this corner on the back upwards, and when you do that, you get into an equivalent, basically the mirror image twisted boat conformation, except that now we're kind of looking opposite in direction, and so you have that crisscross with the bonds, right? Now continue on with that restricted rotation on the bonds, and you can now raise up the pink corner over here to get you back to a half chair conformation, right? So raise it up here, you get to this flat uh, shape on the molecule, and you just have the one corner that's pointing outwardly. And then finally rotate this a little bit more, and then you get these bonds to basically have the corner pointing down, and by doing so you get to the other chair conformation. And the whole point right here is to highlight that the equilibrium is not that of you rotating the molecule on its own axis. It's actually the rotations of the carbon-carbon single bonds themselves that, through this entire energy profile process, leads from one chair conformation to the other. So in essence, what this is going to mean for us is that the leftmost carbon on one chair conformation is always going to be the leftmost carbon on the other chair conformation. And same thing here, the rightmost carbon on the chair conformation is going to be also the rightmost carbon on the opposite chair conformations. And this is a direct result of the bonds rotating somewhat, leading to the various intermediate structures that you see here to yield the other conformer, right? If you simply were rotating the molecule on its own axis, then the rightmost carbon will no longer be the rightmost carbon. And this is a huge point to be made, because we're going to utilize that to ultimately come up with the two conformers. So let's take a look at some examples of this process. Let's say we're dealing with cis 1-ethyl 2-methyl cyclohexane. So you may recall from our previous lecture that if you have a cis conformation involving cyclohexane, what that means is that the groups other than hydrogen, so the methyl and the ethyl, they both have to be above or below the hydrogens. And notice here, methyl is above the hydrogen, ethyl is above the hydrogen. So this is your proper cis conformation. Now what we're going to do is, in order to draw the conformer, right, first of all, we noticed on the left we're pointing down, on the right we're pointing up in the original conformation. So on the other conformation, left points up, right points down. So get used to drawing these cyclohexane conformations, right? So you start down, work your way up, start up, work your way down. All right, now, as I pointed out before, the leftmost carbon is still going to be the leftmost carbon on this structure. The rightmost carbon will remain the rightmost carbon. And the other thing to point out too is that this section of the cyclohexane molecule is the front portion of the molecule. That will still remain true. This will still be the the front portion of the molecule, while the portion here is what we call the back portion of the molecule, and it will remain the back portion of the molecule. So keep that intact, right? Don't start messing with that, because you'll get confused really quickly and your structure will end up being wrong. All right, so this is what happens. Looking at the structure right here, this is the rightmost carbon, the carbon that goes to the farthest right. If we look at the structure and try to locate the carbon on the rightmost end, we'll find out that this carbon over here is the rightmost end. Also notice that the ethyl group is positioned on this carbon, which is on the front part of the molecule, but it's one carbon to the left of the rightmost. So we have to look at this conformer from the same point of view. We look at the rightmost portion of the molecule, we stick to the front side, and we move one position to the left. All right, so just to kind of reemphasize this with the color, rightmost carbon, that's where the methyl is located. This is the rightmost carbon, so here's where the methyl is going to go. And remember, you want to draw your axial bonds pointing down or up. If the corners are pointing down, the axial bond has to go down. And then you draw your equatorial bonds so to complete the tetrahedral shape of that carbon as best as possible. Now, because we are dealing with a cis conformation where the methyl group has to be above the hydrogen, you better make sure that your methyl group still remains above your hydrogen in the next conformer, right? So it's not only about figuring out where the methyl is going to be bound in terms of this new conformer, but you have to keep the configuration the same. Methyl is above hydrogen, methyl better be above hydrogen here. And then, as I said, the ethyl group here is on the front part of the molecule, but one position to the left of the rightmost carbon. So over here, we're going to be on the front part of the molecule and also one position to the left. So we're talking about this carbon right there. And since the ethyl group was above the hydrogen, it must remain above the hydrogen in the structure. Now, ultimately what this means is that groups that used to be axial in the original conformer, so the methyl group and the blue hydrogen, they are now equatorial. And the groups that used to be equatorial in the original structure, so the black hydrogen and the blue ethyl, they are now axial. Blue ethyl is axial, black hydrogen is axial. And this is the overall outcome of the conformational change of the molecule. It's all based on keeping the left and right portions of the molecules intact and making sure that you don't accidentally place your methyls on the wrong carbon. Leftmost carbon must remain the leftmost carbon, rightmost carbon must remain the rightmost carbon, the front side must remain the front side, and the back side must remain the back side. All right, so in terms of Neumann projections, you could look at the carbon-carbon bonds, in this direction, basically to kind of incorporate the non-hydrogen group, so methyl and ethyl, right? So that will take place via these bonds. Now, in the case of cyclohexane molecules, the structure is going to look a little bit more complicated than what we've seen in the previous videos. But what we're going to ultimately find out is that the energy profile of these two conformers is not exactly the same. And what that also means is that we might be able to find out which one of these two structures is the most stable. And also, we might want to find out what are the equilibrium amounts that we're going to have of these two conformers present in solution. So this will mean that we're going to have to look at the torsional strain of the conformers via Neumann projections. And we're going to do this in the next video. So I'll stop the video right now and I'll see you in the next one.